this is a strange circuit and a strange situation and a strange effect that I noticed it while I was trying to make a protection for the gate of the Mosfet. So this circuit is to protect the gate of the Mosfet. That's the intention of my experiment that I'm doing here. This is the circuit diagram. That's the Mosfet gate drain source, internal diode of the Mosfet, 100 kilo resistor from gate to source or to the ground, and 1K here, because 1K and 100K, these are two resistors and they are forming a voltage divider. And I actually looked into my calculator, my voltage divider calculator that I made, and also I looked on internet as well to be perfectly sure that my calculator is good enough, and it was. So 1 kilo here and 100K there is giving me 11.88 volts division from the voltage division here, from the 12 volts that I'm inputting there. I should write there. So there is 12 volts that is getting into this 1K and is powering this gate to the ground. is powering this voltage divider pretty much, and in the same time is powering the gate. And from here, actually I didn't complete this. I should maybe put. So from here, I'm from this side I'm powering with 5 volts through a 10 ohm resistor, through this one at 5 watts, and through drain and source at 5 volts. Actually at different values, but for now I will stop. I will limit everything to 5 volts just to, because this is I get a very strange effect, and it's extremely strange, and you will see it in a second. I will explain everything. I actually built exactly the same circuit twice here. This was actually the first circuit, and I noticed something, but I wasn't really that sure what it is, because everything is cramped, everything is super close together, and this is my way of building stuff when it's a finalized version, pretty much, not for testing. So I said it's exactly the same circuit as it is here, or this one. And I said I need a little bit more space, larger space, bigger space, to actually be able to change if I'm burning, because right now this is in testing mode, and if I'm burning this motherfucker, to be able to change it very quickly without being obstructed by this resistor and this diode there. As you can see here, everything is very, very close. Yeah, you see, and probably there is a resistor, and it's very, very close to these pins, and when I'm trying to desolder these pins, the resistor is also flying out, and this is the diode there, and here is another diode. And it's very, very tricky because it's very close together. So I push it aside, that version, and I build another one with very, very big pads and generous space, very generous, to be able to put my very worked out, the tip of my solder iron is very eaten and is very bond, is very round right now after a lot of working with it, and it's not for very small stuff, especially to change it. It's I need space, a lot of space for this tip of the iron to get in there and do its job. So that's why this version that I'm having here. Actually, this resistor gate here was the last thing to add. I didn't plan for it in the beginning, but that's why it's good to work on cardboard and with this kind of sheet metal pieces that these are scrapped metal pieces, and that's why it's good, because you can practically dance and do whatever shapes you want. And this was a bit more tricky to make because let me not put my fingers there actually. Because I was not grounded, and now I put my grounded strap on, so now I can put my fingers there. That's the last resistor there that I didn't plan really for it, but I did it for protection, mostly from a protection point of view. These are the values that I came with in the end. I watched and I looked and I literally hunted for any protection circuit for the gate of the Mosfet, and all that I could find was these two diodes that are put in this way, from source towards gate and from gate towards drain. Actually, this is a circuit, and I will probably show it in the editing version of this movie. I find this version of protection inside a Mosfet, and I find a very few version, not that many as I was expecting actually. I was expecting Mosfets today to have more SD protection inside them, but really they don't. And I was a little bit annoyed and frustrated, because you should get protection in Mosfets. We are advanced enough as a human species to add more protection from here, especially from SD electrostatic discharge. You know, these are bare naked, like they are made like this, without any kind of protection. And this is my goal here, to find a way to protect their tiny asses, pretty much, not to get burned. So my power supply is 5 volts there, and I'm using again my ATX 12 volts power supply from here through this switch, which I didn't draw it there, but from that 12 volts is a switch, and then to that 1 kilo, and there is the 1 kilo. You see it? There is a SMD there, and this is the wire 12 volts, and this multimeter is on the drain source, so it's here in drain source connected, and this other multimeter is from gate. You can follow the wires. It's from gate to source is connected, so it's directly on the gate there and here on the source or on the ground. So that's how I hooked up my two multimeters here. Good. My negative wire is out from that power supply, And this power supply is off. I have a little bulb that is announcing me that is on. I can show you. See, when I'm plugging it in, is lighting up there, and when I'm plugging it out, is shutting off. Actually, let me take out. Yeah, you see the voltage on the gate. It charged up. Probably it's a capacitor here, and now is discharging, or is the capacitance of the MOSFET itself. I'm not completely sure what it is, but and check this out. And check these two multimeters. You see? So right now, pretty much it is not charged. I mean, this MOSFET is not. Its gate is not conducting anything. Is off, but it is showing these two multimeters in tandem in the same time is showing some voltage there, some very small voltage, and it will get even weirder than this. And I didn't expect it. Either this MOSFET is already busted. I should try other MOSFETs that I have in my box here. This is my resistor box, which I requested a green one, and they sent me a pink one. Yeah, well, and it remained like that. That's for the resistor, and here is for other components like diodes, chips, integrated circuits, and transistor, of course, and mostly LEDs, because this box was originally for LEDs, and then I put other stuff. So I should probably change that MOSFET with another one in the next exercise. But so this is brand new, absolutely from my box, from this box. It is conducting good enough when I'm performing the normal test. This is the normal test that I'm having it here from my power supply. I'm providing with 5 volts. My power supply amperage is showing 0.47. Let me actually power everything and show you this, the normal way of functioning. And it should have been, yeah, probably this is fucked up, maybe. Yeah, I know. If I'm shorting the gate, yeah. Let me short it again, the gate to source. Yeah, I see. Yeah, well, for some reason it's charging up to that, but it didn't. So this is what I'm doing. I'm shorting the gate to source with this tweezer, and it is shutting off my transistor. Now it's 1047, and now should be off. Maybe my transistor is fucked up, but most probably it's fucked up. Nah, I'm getting all kind of, or is because of these diodes, these two diodes here, especially that one, this one that is here. But I wanted to show you when I'm powering, I'm getting the normal value. When I'm closing the gate, is not. It was something else before. Now it changed. Okay, so I modified the circuit. I raised this diode that was from gate to drain. I also took it out from the circuit. There it is. That's the diode. It's a SMD diode, and it was pointing towards drain here, and it was adding some very, very erroneous behavior in the entire circuit. At the point I was thinking, very serious, that this MOSFET is busted. So I took it out, and now everything is working as it should be, very correctly, very normal. So there is my 5 volts. Here is my 12 volts gate voltage from my ATX here, and this is the switch. Because the gate, you see, it's 0 volts because I'm having this switch closed, and when I'm opening the switch, I hope you can see both. Yeah, you see, it's changed to 1193. Actually, it's 12 volts, and when I'm closing it, is literally I'm cutting the 12 volts line from there to there, because this wire here is through this switch. So when I'm switching here, I'm giving 12 volts, and this is reading 12 volts. And here, this is reading 5 volts when the gate is off, as you can see. On there as well, 5 volts and 0 amps, because right now the MOSFET is closed. And this is the normal behavior, what it should show normally. It shouldn't flow any kind of current through the amperage there when the gate is off. And when I'm tuning it on, the gate, this is going to 0 potential between the drain and source here with a tiny little bit of voltage, because this resistor is dropping a little bit of voltage across it. This is practically a shunt resistor, and that's the voltage that is getting on that, but it should be 0.000. And this is showing that 0.48 basically over the transistor, over the resistor, over this shunt resistor is getting that amperage, is flowing through my transistor here. And this is the correct behavior, the normal behavior, 5 volts, 0.47. You see 0.47 from my power supply unit. It means what my power supply unit is providing, 2.35 watts. And here over the resistor, the wattage is 2.15 watts. And the wattage over the MOSFET is 21 milliwatts, what I'm getting there. And because I'm grounded here, I can actually put my finger over the MOSFET and feel if it's hot or not. And it is not. It's not even warm. But everything I created here is just showing that is working normally, and it proves, at least it proved for me, that this diode is actually inserting a lot of errors in the circuit here. It got me to the belief that the transistor itself was bad. So let me close it, and here, there you can see it changed. And when I'm switch it on, off, on, off, on, off. You see, it's switching correctly. Everything is fine. And also here, or here, both of them, you will see it changing when I'm switching the switch here. See, off, on, off, and on. You see? And off again. This circuit is showing that the MOSFET is good and it's fine, and it also proved me that fucking diode, this diode here, is not good. It's not good to add it here because it is inserting all sort of bad elements. It's adding some errors to the circuit. My guess, it is interfering with this diode here from source to drain that is pointing like that. This is like a bigger diode. Is formed from these two diodes, and for some reason is keeping the gate open for some reason at quite a high voltage when it should be off. When the switch is off, like it is right now, it is still charging up, is allowing the gate to charge up to a certain voltage, and is opening the MOSFET, and the MOSFET is conducting all this power over that load resistor, and is heating up. Actually, I catch it quite hot at some point without any voltage on the gate, just staying like that without being activated, pretty much without normal activation. So that's a big problem here. That's a big problem. This is not a problem, but that was a problem. It's a very interesting. Or maybe this must be very special diodes that you must insert here. I don't know, not to create this erroneous behavior that I observed. And I don't know what kind of diode it may be. These diodes that I'm having here, they are not that special. Is this one. And you can search it yourself on the internet. Its name is TS4148. It is practically a 1N4148 equivalent, but it's 1206 size, and this is from its datasheet that I find. The white line is the negative, the cathode, and anode is the positive here, and that's it. It's a very cute one, very cute. I actually looked for them. I actually searched for 1206 diodes, not for this model. I only needed a 1206 type of diode, and I have another diode, but it's not 1206. Is this more fatter one? You see, this is a Schottky diode. This it's a simple rectifying diode. Let me actually test with one of these here, and let's see if I'm getting that strange behavior. I don't know what to say. What I'm saying here, what I believe the problem is, and I'm repeating myself, I believe this diode is seeing this other diode that is formed here, and these two diodes in parallel is creating some sort of gate enabling, adding a little bit of voltage to it. I did see a 0.6 or 0.7 volts on the gate for some longer time actually, and that's how I deducted it must be one of these diodes. I wasn't sure which one, but my money was on the top one for some reason. I don't know, I cannot explain, it's just my gut feeling, and I was right. I was perfectly right. Let me actually test with the Schottky one and see what will happen. Okay, I changed with this diode. Is this one SS24 Schottky diode, SMD. I'm getting again some weird values and weird responses, but I'm getting the normal switching mode. You see 040 amps or 400 milliamps, and this is off, on, off, on. Remember, it was 047. You see it here. This is the normal. For power supply amperage, it was showing 047. Now is 040, a little bit less. But here, this is the most important voltage reading that I'm doing here, gate source, and it's showing only 1 volt when it's on, activated, and when it's off, it's showing 0.4. It's not 00. Or is decreasing? Yeah, probably it is decreasing because I'm having this 100 kilo maybe. Yeah, it is decreasing indeed, but it's not good that it's holding that voltage there. Let me actually short it out like this. And if I'm shorting, yes. Yeah, you see, it's rising up again immediately after I'm getting the short. You see, this is shorted, and now when I'm lifting up, it's getting up. Yeah, see, it's raising the potential for a little bit. All this time while I'm making all these tests, I am grounded here to my iron table. You see, it's made from iron, and this is the ground wire that is going there. Okay, so this other one is showing me 5 volts when it's off, and it's showing me 0.7. It should have been 00, but 0.7 is a diode forward voltage, and I bet it is this one. So I changed this one from gate to drain with this Schottky one, but I leave this other one here. Let me change this other one as well, which is here. You can see it there. This is the diode. Okay, it's a pity that I cannot use these SMD diodes. And it's an eye-opening that normal rectifying diodes are not actually suitable for protection, for MOSFET gate protection. Let me change that diode with this Schottky, and let's see the results after that. Okay, so now I changed this diode from source towards the gate with a Schottky diode, as you can see, the same as that one. So it's this one here. My ATX power supply is not powered, so also the gate is not powered, but I'm getting exactly the same behavior as before, 0.77 voltage gate to source, and it shouldn't be this any kind of voltage. It should be 0.00, and here I'm getting a little bit less than 5 volts. It's showing a little bit of amperage that is surging through my circuit here because I'm getting this very low voltage on the gate, less than 1 volt, a little bit less than 1 volt on gate source here, which again is very strange, and it is because I'm having this secondary diode. That's the problem. This one. Let's power the gate, my ATX power supply here. So now my switch is off, Let me film like this, and now is off, now is on. And here is should be 0 0, and here again I'm having 1 volt, which is very weird, and it shouldn't. It should have been 12 volts or close to 12 volts. And here is 0.4, exactly the same as before when I was having this one. This diode was 4148 diode. Yeah, it's a very strange behavior and very strange results when I'm having this particular diode here. So it doesn't matter what diode I'm having here on the source gate. If it's this rectifying diode or this Schottky diode, doesn't matter. All that matters is this diode not to be here, is the one that I erased from there. It shouldn't be there because it's creating all this mambo jumbo. It's literally mambo jumbo here. And there, let me close it actually, because now this is mambo jumbo. It shouldn't be like this, and it shouldn't conduct that. And yeah, it is conducting a tiny little bit, which is this voltage is the most erroneous voltage. This voltage shouldn't be at all. It should be 0 0 when the gate is off. Remember, the gate is off. If I'm powering off from here, you see, it still remains the same. It's like switching from there. My power supply is not working. It's still remaining like that. If I'm shorting gate to source with my tweezer here, basically adding a 0 volts directly to the gate. Let's say it's this gate is charged for some reason. You see, it's 0 there, and the moment I'm lifting up, my tweezer is rising up again to that inconvenient voltage that is keeping my MOSFET open. And it is not hot, but this is hot. My resistor, it is hot. It's getting some voltage across it. Something is getting, and is not hot, but is warm. It is warm. From that little voltage, from that little amperage that is surging there, is adding up. Let me actually calculate it a little bit. I did some calculation for the other one before. When the switch was off, I was getting this data, voltage gate to source, but I didn't add it in calculation. But I noted it down. It was 0.96 when the switch was off on the gate. The voltage drain source was 1.35, and I got 459 wattage over the MOSFET. And also when the switch was on, 560 watts, and the resistor was crazy hot. It was very, very hot. So I had to unplug it literally to take out the power from there to shut it completely off, because it was keeping everything live without commanding it, and that's not good. And here is not good as well. So let me take out that diode and see if everything behaves as it should be. Okay, so now I took exactly is this circuit without this diode here. I took it out, is there, and let's power everything, and let's see if we are still getting some crazy some crazy values here. Why I'm getting that? It shouldn't. Maybe the transistor is busted. Let's see. Yeah, 005, 08. Very strange. And let's see if I'm shorting it down. It is shorted and it's raising back. Motherfucker. It's raising to 0.8 now. And when it's on, it shouldn't be that. Why the fuck? Maybe the transistor is busted? Motherfucker. So, I managed to burn other 2 MOSFETs, and I didn't realize it, and that's why everything was working like shit. Here I was getting all these values. This is the 3rd MOSFET that you are seeing here. The first one that I didn't realize, then I switched the MOSFET with another one, and I made the mistake of burning it without realizing, and after that, I changed that one with this one that you are seeing right now. And while I was changing this one, I was calculating the mistake that I did. As you can see, right now it's working fine. When I'm switching from here, everything is as it was before. You see that, and this is on. Right now I activated the MOSFET, and that is showing almost 0 0, and this is almost 12 volts as it should be. And there is 0.48, 0.47 as it should be, and now is off 0, and 0.48 and 0. And before, when I was switching off, instead of this 0 amps, it was showing 0.37 or something like that, 35, 350 milliamps, just having the gate off. And here it was also showing some voltage, 0.7 I believe it was, or 0.7, and here also a strange number instead of that 5 volts that you are seeing there. And this is, again, I'm switching it on, and this is off, and this is reading correctly 12 volts there, and everything is as it was before. But the mistake that I did, I turned off my power supply there. After I turned it off, I soldered the MOSFET. The wires were connected to the circuit, and then I turned on the power supply, and in the moment I turned it on, it created a spike, probably, that it burned my second MOSFET. Also the first one, because I did switched off my power supply. Most probably, I don't remember when and in what conditions, but I did. Most probably I did. So if I'm turning it on, and let's see, hopefully nothing will go bad. No, it's good. So right now when I'm shutting gate source, is practically I'm shutting off and turning off and turning on my MOSFET. This is turning on when I'm out, and when I'm contacting it, it's turning off the MOSFET when it's to the ground. And there is everything is okay. I was thinking maybe because I did this thing with my tweezer before, I was thinking maybe I damaged it somehow from this exercise I got used to do it. And this is on and this is off, on and off. It's functioning very well, with the exception of turning off the power supply and turning it on. So I really need a protection against my power supply when it's turning on and off from the button, and also from voltage to amperage when it's switching. And I believe it might be the same thing as turning the power supply off when it's switching from voltage to amperage, and from amperage to voltage back again when I was having that short circuit mode. When it's switching from voltage to amperage is entering in short circuit mode in the protection mode of the power supply. That's what is happening. And when that is happening, is blowing up my my MOSFET in test. So this is the secondary problem when I'm turning off my power supply from there. But I will not do it because I know for sure it is. And I don't want to show you this. Just try to believe my words when I'm telling you, because this is my observation. I'm very sure is because of that. So I really need, what I really need in this circuit here is a spike protection of some sort. Here on the drain, before the resistor, somewhere here, a protection circuit for spikes, for high voltage spikes. And I have no idea what it may be. Maybe from here to here, from source. Maybe this will add some sort of protection if I'm inserting here a diode from the negative rail to the positive rail, pretty much. Exactly like this diode here. Probably, you know what? Most probably this internal diode of the MOSFET blow up when I was doing all those testings before. It might be. Very interesting. Let me actually test this. Alright, so I've added this diode here from source to drain, and here I don't have any diode, and there I don't have any diode. So I don't have here from gate to drain, I don't have a diode, and from source to gate I don't have any diode, but I have from source to drain. Here I added a secondary diode in parallel with this diode, pretty much. That is internal of the MOSFET. And let's see what this will do. And I did started everything here. I did a little test and everything is working fine, you see. And there as well is working fine, 0.47, good. And let's do this test. I'm turning it off, my power supply. And that is showing a capacitor discharging there. That's my drain source voltage. Exactly these two wires, exactly this power supply voltage. And now it's off. And now when I'm turning it on, it's bang. Okay. Okay. And now it's good. There is good. It is good. I swear to God, this was a very big problem here when I was turning on and off my power supply. And let me do it a couple of times. Actually, I'm turning off the gate, on the gate, off on the gate, and it's doing fine. Actually, let me leave the gate on in conduction right now. My MOSFET is conducting all the stuff. I'm turning it off. And it is showing off probably there. And now when I'm turning it on, like that. Okay. And let's see, power off. All is good. Everything is good. Good enough. It is good enough. Oh, okay. So this is very interesting problem. From drain to source, most probably that diode was blowing up internally. Very interesting. Okay, let me add again those diodes here, because this test for the ESD problem, electrostatic discharge problem, and my belief is this diodes will solve the problem. But let's see if I'm having the same problems as before. And I guess this diode here, was preventing me before doing normal experimentation with this ESD protection diodes that I started with. All right, let me put those in circuit and see what the readings are now. All right, hello everybody. Hello from your favorite artist electronist here, Mr. Q12, with a new and exciting subject and movie about how to protect the gate of your MOSFET, especially against ESD problem. ESD stands for electrostatic discharge, and I had this problem all my life when I was dealing with MOSFETs especially. Let me show you this. This is the most used MOSFET that I made most of my experiments, and all those dead MOSFETs that you see there are also, there are a few here. So there are a lot of dead MOSFETs here. They're like flies. I mean these little ones, also those ones, but those doesn't count. Only these ones are dead here from this experimentation that I started here. And all of those are this A09T MOSFET, which is sensitive enough to ESD discharge, ESD. But so this one, 3N702, or abbreviated 702 is the marking on it, they are way too sensitive. They are extremely sensitive to ESD. And they are also MOSFETs, they are also N-channel, but they are extremely sensitive, and is exactly what I'm having right now there. But until now I did all the experimentation with this type of MOSFET. Only one MOSFET like this I'm having it right now there. Why? Because I'm having an extremely sensitive gate on this type of MOSFET here. This is also sensitive, but this is even more sensitive. I cannot explain in words how the difference, how the sensitivity is between them to compare them. But they will shit it. They will die just like that. If I'm blowing air over its gate, it will die. That sensitivity is. But this one I have to, it's a bit more resistant. If I'm touching it 1, 2, 3 times and then will die. But this one, if I can get close enough to its gate, it will die like that. They are fantastically sensitive. So I'm working intentionally with this sensitive MOSFETs that I have and that I know their characteristics. Again, this is the only one that I'm testing right now that's sensitive. Until this one that I'm having it here, I use that A09T model. And I'm conducting this experiment for a week. So this test setup that you are seeing it here is in a week time used and abused and changed, and I did a ton of experimentation, a ton of changing of components, and of course burning a couple of them. There are not so many. I don't know, maybe 10. I didn't stay and number them. Let me see. 1, 2, 3, and that's half of it. Yeah, it's 13 of them. It's not that much, but the good thing is that I discovered something, and I'm very happy now. Even if I burned all those fuckers, it really helped me find a solution to this particular problem. And I will show you, I hope I can show you all the tests that I did. At least I will show you the most important ones, because I did, like I said, a ton of testings, a ton of changing. I changed the shit out of the components here for protection around the gate. And it's not only the gate, it's the source. So this is the path from gate to source. This is when the transistor will get damaged from the gate to the source. But it's also true from the source to the gate. So in this other direction, it can blow up the MOSFET. So if I'm having too much potential here and lower potential here, this higher, very high potential in order of thousands, 1,000, 2,000 of volts of electrostatic voltage or energy, it will crack, literally crack the very fine insulator inside the MOSFET, and it will puncture it, and it will gap it, it will get through it. That's how the MOSFETs died. And so from gate to source or from source to gate. But in all this experimentation, I was concentrated only from gate to source, this path. So from this direction towards this side of the MOSFET to make the a proper and secure protection. You see here some erasement. I erased some stuff because I will erase and I will add the proper diodes, and I will exemplify there while I will do the test, and I will show everything. I hope I can replicate everything that I did. I had here a SMD component here instead of this 1x8 power resistor. I changed that SMD resistor that I had with this through hole one, because the SMD resistor, its pins got damaged and it didn't make contact. It cracked because I moved, and I moved a lot. I changed a lot, and I managed to crack one of its pins, and it gave me a ton of errors. And then I changed this 1 kilo. It's this 1 kilo that you're seeing here. So this is the 12 volts from this wire. It's getting to that 1 kilo into the gate. So to be clear, I will concentrate in all these testings that I did here. I was concentrating to protect the gate from higher spike voltage SD voltage on the gate towards the source. So that's my concentration, but also towards the drain in the same time. So in this direction and in that direction to surge whatever is accumulating there potentially, you know. So I hope it's clear as mud. And let's do the business. Like you're seeing here, I actually wrote the testing MOSFET that I did all the majority of tests. This is an exception what I'm having here, a tiny little bit of exception, but really is not that big of a difference from this one. In terms of wattage, voltage, applied voltage, the current that is passing through it, it is a tiny little bit of difference, but it's not that much. It's not that important. So from this perspective, they are quite the same. From electrical point of view, they are quite the same, and power point of view, of course. These two models. So yeah, enough talking, more doing. The very first test that I really seen a protective help was this diode that you are seeing it here, this one. And this is a Schottky diode, and it's here, is in parallel with drain source, and also the inherited diode inside the MOSFET. So it's in parallel with that, and it is, my best guess, it is helping that weaker diode there, is helping against some spikes, especially when my power supply is starting. I destroyed 1 or 2 MOSFETs, and after I put this secondary diode here, which is that one there, that you can barely can see it probably. Yeah, now you can see it clearly. You see it? This SS24, and this is 702. You see the marking, and this is 114. It means 100 kilo, 110 kilo maybe. Yeah, that's a scrapped resistor actually, that 100 kilo that I'm having there. That's the only visible modification when I've added this diode, that it is indeed helping the MOSFET not to blow up in this special circumstance. And I'm keeping it all the time there. This diode, I'm not changing it at all. I will change only this and that. So in the very beginning of all my tests here, I did all the experimentation with this type of diode. Not that, with this one, with this type of diode, which is the equivalent of 1N4148, but this is the semi-day version of it. You see how they are looking. And I didn't get any good results. In all the tests I did, it didn't work as I wanted it. It worked kind of, but not really. And if I'm inserting this type of diode, let me draw it here. If I'm inserting it here, it actually is not doing anything correctly. It's actually protecting, or better said, it is dumping all the high voltage that is accumulating on the source pin into the gate, but is not allowing any kind of voltage to pass from the gate to the source in this direction. So pretty much I'm forcing the gate to fry when I'm inserting this type of diode, this rectifying diode in this modality, in this position. And I found it in one of the protection circuits diagrams in the internal diagram of a MOSFET. I will put a picture of it. That's actually give me a little bit of hope. And that's why I started all of this experimentation that you're seeing here, because I've seen that normal diode there. And I didn't think too much at the beginning, but now after all this experimentation, I start to think a little bit more in depth, and that's what it's doing pretty much. And it's not doing the right thing. It is not correct to have a normal rectified diode there. It needs a special diode there. I got to that special diode. I really find it. For this protection, specifically for the gate, we need a path to the source to dump all that high voltage from the gate to the source, but in the same time onto the drain. So we need another diode here from gate to drain to dump all the high voltage accumulated on the gate, potentially. And this was the biggest problem to deal with. This was easy. From gate to source was kind of easy. It kind of worked with any diode I put there. But this one, gate to drain, it didn't work at all, and it gave me a ton of errors. And I will show some of them. Like I said, I did try it with rectifying diodes as well, that 4148, but is literally diverting this 12 volts into the power supply, this other power supply here into the drain, and it's making a mess, and it's not doing what is not letting the MOSFET do what it is supposed to do. So it's interfering if I'm putting it there. So it's not good. If I'm putting it in this other sense, is again like in this case, I'm dumping all the voltage from the drain into the gate, and again I'm forcefully burning the gate. And I tried, like I said, with rectifying the diodes, and it didn't work with any of them, especially those 4148. And then I changed to these Schottky diodes, which is exactly the same story as with the rectifying diodes, those 4148s. But this Schottky diodes, SS24, this one. So I repeated all this experimentation, the same thing that I did here with the 4148, I did with this SS24 Schottky diodes. The same procedure, I changed everything, and exactly the same results I got with the same errors and the same disturbance. I disturbed the functionality of the MOSFET by inserting them in other way, especially here from gate to drain. So let me actually demonstrate with this one. I will put it exactly from gate to drain, just to see the effect, what is going on and how it's behaving, just for the kicks, And let me unpower it, because right now it is powered, and I'm putting my protection here on my hand, this strap to the ground here, to protect the gate of the MOSFET when I'm working on the gate there, when I'm soldering this. So I'm pointing. My diode is exactly as here in this diagram, is pointing towards the drain, from the gate to the drain, and you will see what is happening. And then I will change its direction in other sense, and you will see what is happening then. This kind of experimentation that I'm doing here, it might seem stupid, but it's good to see how stupid looks. And trust me, it will be good to see all this stuff. Anyway, I'm having 5 volts here, 5 volts here in this side, and 12 volts here. And let's power on my ATX power supply here. So now I'm getting 12 volts, and when I'm changing, I'm opening the MOSFET right now, I'm getting 3 volts there and 3 volts here. You see? Because this diode is conducting in this way, like this. And it was the exact same behavior with the other diode. So I don't have to repeat. Is enough to make this test with only this Schottky diode, because it's telling exactly the same story as with the other one, with that rectifying 4148. This is the error that I'm getting. So this is 5 volts across the MOSFET when the gate is off. So the gate is off, and I'm getting this 5 volts. And when I'm opening the gate, I should get 12 volts here, across gate and source. These two should get 12 volts, and this should get 0 volts, or very close to 0 volts. And let's do the experiment again, and I'm getting 3 and 3. Here should be 12 volts, and here should be 0 volts, or very close to it. And it's erroneous. This is interfering with the functionality of the MOSFET. So it's not good. Good. Let's inverse this diode. Let's put it inverse. So like that. In this position, so this 5 volts, practically it will surge into this gate. It will add to this 12 volts. Okay, let me interrupt this 5 volts. I know you cannot see the marking on it, that line. I can barely see it, but I can see it, and I know exactly what I'm doing here. So I'm doing it correctly. Okay, so now it's pointed this way. And I'm getting, only by connecting the 5 volts is actually powering the gate. And I already have 200 milliamps through this circuit. And let's power this other circuit, the actual gate with 12 volts. And I'm getting 12 volts there. And here it's changing to 380 milliamps. And this is off 200 milliamps. And this is on 400 milliamps. So this is the interference that I'm getting. When I tried all this time to add a complete protection for the gate, especially from the gate to drain, that's the entire point of this experimentation, and why I put this diode in all these positions, and I showed you all these errors that I'm getting across the MOSFET. And again, I'm repeating myself, this Schottky diode, this SS24, is telling the exact same story as when I put that rectifying diode 4148. Is exactly the same story. So now I will take it out from here because it did its job. Finally, good. This model of diode is very good. It's very good model. You can solder it and unsolder it many times from these 2 leads. If you bend the leads 1 or 2 times, it will rupture, it will crack from there. So it's better to leave it as it is, not to bend it too many times. But other than that, is fantastic. I changed this diode probably 20 times, probably in all my experimentation, and it's behaving as it should be, as it was like it was new. And let's power everything on again and test, this time without any kind of protection actually. So here I'm not having anything, and also here I'm not having anything. In this circuit that you're seeing here, I'm only having that resistor there, this one here, but this is no diode here, no diode here. And let's see, without any kind of protection, how it's performing. As you can see, it's showing there 5 volts 00 amps when the gate is off, as it should be. And when I'm powering right now the gate, I'm getting 12 volts gate source here, and here I'm getting 1 volt. This is a little bit of difference from this MOSFET to that A09T. This is the only difference here. On this A09T, I'm getting much more lower voltage here, like 0 point something else is much more lower than this 1 volt, if I remember right. I hope and here it was showing actually 0.4 exactly. This particular MOSFET is running as it should be, is running correctly at these parameters. So now the gate is off, 0 and 5 there, and now the gate is on. I'm opening the gate, 12 and 1 there. This MOSFET is getting very, very hot with these parameters that I'm having here, a bit more hot than this A09T, and that's why that 1 volt that we are seeing here is probably having a little bit more resistance, it's having more RDS on resistance than that one. Most probably, I will have to check this. If I'm putting the diode from source towards the gate, it's not affecting anything. The functionality of the MOSFET is fine. But if I'm putting it towards the source, it will dump, it will practically make a short from 12 volts to the ground, and it will not really. It will conduct a little bit the MOSFET, but not really. It will not conduct the MOSFET at all, because it will create a short path, and that's it, end of story. So I really was in panic that I could not find a solution for this problem. And after all this experimentation with the normal diodes, well, the rectifying one, the 4148, and this SS24 one, a Schottky diode, it took me a couple of days, 3-4 days, to do all this stuff with breaks, with thinking about it, and I said, fuck it, let's do the stupid things anyway, and I did it, and yeah, it didn't work at all. And I was especially upset. I was very, very upset on this gate to drain side, because this is the most important side probably. Well, both sides are important, gate to source and gate to drain sides, and to cover them, to make the possible over voltage accumulation here, to drain, yes, to drain on the drain and to drain onto the source, to leak very easily there and there, and not to leak inside this junction here. This pretty much protect that junction. I looked on internet, I made some breaks, and I thought on other stuff, and then it occurred to me, well, I didn't try it with Zener diodes. Why didn't I start with Zener diodes? Why? Because especially a very important thing I continued. That's why I lose so many days of experimentation, because of these fuckers. So I took these diodes. You can see the markings, the sign, how they are designated like that. That's the symbol. So I spent a lot of time with this type of diodes. So after I finished with these normal ones, I was looking on other transistor protection diagrams, and I've seen this symbol there, this TVS symbol, and I've read about it, that they are actually using this TVS diode there inside, and it was exactly like here. It was here and here in this location, covering these two sides, or only this side and this one not. But I really liked a complete coverage of gate to source and gate to drain. So let's put this TVS here first on source to gate. This is a bidirectional model of diodes that I'm having. You see, it's having this marking here is saying KA. So this A is unidirectional, is only having only one diode there. But this QA, it means bidirectional, is having two diodes head to head, and this is the symbol is like that. So this is the model that I'm having here. All of these values that I'm having are this bidirectional QA model. I bought this specifically for this problem that I'm having it for a very long time with SSD protection. This is a small circuit just to remind myself very quickly how to use it, how to test and how to read this diode. If I'm losing track of one diode like this, how to test it. So this is a small circuit for testing. Here I'm putting the oscilloscope probes here and here. And here I'm powering it with 20 volts alternative from my variac or in DC mode. So I'm getting the same value on my oscilloscope probe. So for a 5 volts TVS, I'm getting 15 volts peak to peak on my oscilloscope reading there. So yeah, it's not perfect, the exact value that I'm getting there. At least I have a small test. And I don't remember what I used, which one I used. I believe I used this 20 volts one. I know for sure I used, and this 9 volts probably. Here on the bottom I use this 9 volts. By the way, I made these small boxes because they come in this type of package, and I routed the value there. The problem is that this is the problem because I put some legs on some of them to test them on the breadboard. Some other times, of course, not this time. Like this, you see. And in that type of package, I cannot keep them. Actually, I found a way to keep them, but this kind of packaging, these little boxes, they really accommodate these longer legs, and I'm having 10 of them, so I'm having very little of them inside it. I'm not sure how well you can see. The box is oversized for the quantity of diodes that I'm having there, but I intentionally make it a little bit more bigger in the eventuality when I will add these legs for more of them, you know. So yeah, it took me quite a while to make all these boxes. I hope you find them as cute as I think they are. So I will use this 20 volts. Why this 20 volts? Because I don't have too many values. I have this 12 volts one, but I don't want to use it at this 12 volts that I'm getting from my power supply. Let's see if I can actually find the one that I tested it. Yeah, here it is. This is the one that I tested it. And the rest are the vision. That's all the ones that I'm having there. So this is the very cheap way of holding them there. Very, very cheap. All right, so this is a very special diode, and I spent a lot of time testing it here because that's the diagram that I read in those protection diagrams for MOSFETs. In a way, I was misled because this is not really the type of the diode that they are using there. So they are not telling the whole truth in those diagrams, is my belief. This is not having a polarity, is not having this bidirectional diode this model of diode, this bidirectional one, is not having a sense, a line like a normal diode like that. You can put it, I can put it like that or like that, and it's having no, it's correct in both ways. So it doesn't matter how I'm tuning it. It doesn't matter the polarity of it. Okay, so now it's correct, good. When I'm powering from here, good. This is good. So here doesn't matter, even with this TVS diode here from gate to source, it doesn't matter. It's still reading correctly, it's not perturbing, it's not influencing the operation of the MOSFET. So now I will change here this symbol with a TVS one like this. You see, this is the TVS diode that I'm having it there. But let's put it here in this other side. So this side is covered, it's functioning okay. And actually I will add another one. I was thinking to use the same one, to take it out from there and put it there, but I will leave it there for the moment. So I took another 20 volts. This is a virgin one, because I used other diodes in other experiments, and that's why I don't have two 20 volts that I used. I only have that one. This is how I'm desvirginate them, when I'm bending their legs a little bit, to have more chance of soldering it more correctly. Let's see what the voltages are showing. Good, good, good. Nothing is burned. And this was opened already, and it jumped and it's changed there correctly. And now when it's off, 0 and 5, good. It's good. And now, and also here as well, it's showing that 0.38 and now 0.0 when I'm switching on and off. Okay, so, yeah, what? Huh, very interesting. Very, very interesting. That now it is working with this TVS here. Motherfucker. Before it didn't work probably. So now I'm having here another TVS, so 20 volts TVS, both of them. But I did in my other experiments, I must have used a lower, probably a 9 volts here, yeah, most probably, or 12 volts even, TVS diode. I didn't get these good results that I'm getting right now. Very interesting. but this was not the solution that I found. I found another solution, but this is good enough. This is good enough in the sense that it will protect with these two TVSs. It matters very much what value of TVS you are using here. So this is what I used here and here, and it's working absolutely correct and absolutely fine, and it's switching correct. Huh. Wow. Probably right now I'm let me unpower everything because this is getting very hot, and that one I know is getting very hot as well. Probably I will add here for this one. This is SS. So it can be anything here. SS24. This is a short key, but 4148. It can be this. So it can be any kind of diode there in parallel with here. But I'm also thinking another TVS in parallel with this one as well. So to have two, this one and another one, just to be absolutely sure, you know, super strong protection to have, I'm thinking. And I will explain probably later why I'm thinking, because that very fine isolator substrate is the same thickness also from the gate to source or gate to drain, but also from drain to source as well is very fine. And if I'm getting over voltage even on these two pins, the MOSFET can get destroyed as easily as it got destroyed before I added this diode here. So it's important to add another one as well. There is not bad. It's not a bad idea. But for this thing that I'm having here is a success now, but before I was adding probably less value TVS, like probably the last experiment I put here at 12 volts, probably this one. I don't remember what I did, but it didn't work at all with the TVS diode. It didn't work as well as it worked here for some reason. I don't remember, or maybe the transistor was busted, because I had and I didn't know about it after a long time, after long experimentation. Then I realized, the fucker is dead. Well, it wasn't dead, but it was damaged, and it was giving me shitty errors. So the idea is the value of the TVS that we are using, if it's too close to the powering voltage, either if it's this side of powering or this side of powering, 12 volts or 5 volts, if it's too close to it, it's bad. It will give you errors pretty much. It will not give you a good result like you are seeing here in this experiment. So you have to put something a little bit more higher in value than what we are having, especially for the 12 volts here. And here, if I'm maintaining a constant 5 volts, it's good to add. It's okay to add this 9 volts there, but not 5 volts. If I was having here 3 volts, then that 5 volts I could put it here. So for very, very small voltages, that 5 volts is good there. Now, let me take out these TVS diodes that are okay now. And let me show you my other version that I discovered, and I was quite happy with it. I think these TVS diodes are okay, and they are good enough. This is how you should protect your MOSFET, with this kind of TVS diodes here. But there is another way. Let me show you. Let me take out these ones that I connected them here. And let me actually put them back in their box, because they are a bit strange and hard to read, and I don't want to mix them with those other ones. This is all the Zener diodes that I'm having. These are the voltages for the Zener diodes, and this is the box. And I collected 15 volts Zener diodes. These are here, and so it's a little bit higher than this 12 volts that I'm using for the gate. And I created a TVS diode from two Zener diodes, but you see, I hope you can see, they are both pointing towards there, and this one towards there. This is the black line here, and this is the black line here, you see, and they are both pointing like that, and they are connected here. And this one is just a simple Zener diode, and it will point this way. So let me erase here, and I will erase this one as well, because the symbol for this one is different from that one. This is the Zener diode, this one. So it's pointing towards the gate, but is letting any surplus of voltage going through it to the source. That's its role. And in this direction as well, when something is overflowing here, negative voltage, probably. Okay, you can barely see it, probably, unfortunately, but it is there. And this one, the symbol for this one is different, is like this. You see, this is the symbol. It's pointing in these two directions, and this is the middle point, which is this one. And I created it from this to 15 volts Zener diode, and I will put it here, and I will make this new symbol here, but probably it will not be very visible what the hell is happening here, but it's this symbol because it's too small and I erased too many times there, and it's not perceptible anymore. Now it's linked there, and so is that one. And let's make the experiment again. And what we are having here, let's see, good and good. good and good. Okay, 5 volts here and 0 there. And now the gate is not open. Now I'm opening it and I'm getting 11, 92 or 12 and 1 here. And it's exactly the same result as before. So trust me when I'm saying this is a phenomenal result, at least for me, win for me, to be able to protect, to add more protection to this very sensitive MOSFETs, because this is all about them. How these specific motherfuckers that are incredibly sensitive to electrostatic discharge, to my fingering, to whatever, especially to my fingering, because I'm an idiot so many times and I forget things, and I'm putting my fingers there where I shouldn't. And and I forget things. I forget that these bastards are so sensitive. And I promised myself I will do this specific experimentation and to find a way of protecting it. And I'm very happy now that I reached this stage where I at least I have a way of protecting it. Let me show you a demonstration how I concluded that, how I tested that this diode, specific diode that I'm having here, it is conducting indeed both ways, and it is doing its job for this gate source in this configuration that I put it here. Let me take it out. So before I build it, well, before I put it here, I actually tested it to see if it's doing what I wanted it to do. Let's see. This is brand new. Yep. Okay. Good. So I'm changing it to 15.5. Let's see now. Are you singing? No, not really. Not really. It should have. Let's give it 16. Okay, 16 now. Come on, baby. Caramba. No, not really. Motherfucker. So at 18 there, 18 volts is starting to open, at least in one direction. Yeah, you can see it. All right. And at greater voltage, let's see the maximum voltage actually of this power supply, 31.7, but I have another knob. I should put it to maximum, but is maximum enough to 32 volts. And let's see. Yeah, you see. Yep. Yeah. I hope I will not burn it because it's having only 1 kilo here at 30. Yeah, it's 20 milliamps. It's showing there 20 milliamps. It's good. It's okay, but it's blinding when you are looking at it. So this is how I tested originally this little contraption, this little TVS, homemade TVS diode from 2 Zeners. So now I will put back everything to 5 volts as it was before. See, I will not leave it at 32 volts because most probably I will blow something up here. I don't want to. So this is the original test before I mounted it there, so to be sure that this is actually doing its job. And what I realized with this experiment that I did here, this homemade TVS diode practically, so what I realized is that, I'm not sure how well can you see it, but this diode, this first, when it's getting that 19 volts here, or even more, 32, whatever, when it's getting that higher voltage here on this point, this diode is opening this Zener diode, because this is the sense of opening this in this direction. And this one is like a normal diode, is passing the current through it, thus is performing this this flow of current. And in this direction, in this other direction, is exactly the same thing. When I'm getting over voltage here, over the 19 volts or 32 volts or whatever spike it will be, this will start conduct, and this will behave like any other normal diode. It will let everything pass through it into the gate, unfortunately. But it will save something, and the other one that is here, it will see also a spike of voltage, and it will open and it will probably surge. But let's hope this diode, they'll open more faster than what's inside here, what will open here. But definitely it will protect a little bit, because everything is taking time, even for a spike is taking a little bit time. And when these diodes are put in circuits, it will clip that spike, something like that, and then it will go down. But if these diodes will not be there, the interior of the MOSFET will see a little bit of increase in voltage, but probably it will not be as damaging as without them. That's my mentality. That's what I'm thinking about this configuration, what is doing. And the reverse of it, the TVS symbol, which is more simple to draw, only one here, and like this. This is the TVS diode. These ones that I tested for a couple of days actually. And I didn't get good results with them. Most probably I used a smaller value of it. or what I was getting, what I was having a bad MOSFET there for some reason. But these are exactly the same, is the same principle as this. This will conduct, the first one will conduct normal current through it, like a normal diode, but this diode here is opposing up to 19 volts or whatever voltage is designated. It will open up if the voltage is over that voltage, and when it's opening up, the current is flowing through it. And the same is true for this other direction. So these two symbols are pretty much equivalent, and they are actually Zener diodes. These TVS diodes are actually Zener diodes put head to head, and probably I could put these two Zener diodes also head to head, and it will be the exact same thing as there. Yeah, I'm very pleased, actually, very pleased to this point, but I really didn't actually tested the over voltage situation. I don't know how to test this over voltage spike on the gate, either to drain or to source. I don't know how to manually create it. I'm just adding them there in the hope they will protect the device. And that's it. I will close my eyes and I will pray to God they will do their job, and that my MOSFETs will not die by themselves from now on. And that's it. But me personally, to actually do the experiment, to actually charge the gate with this protection on them, I really don't know how to do it, how to perform it. Maybe other people more smarter than me can do it, but I was actually thinking, but I cannot find, I had a wool blanket, but I don't find it anymore. Natural sheep wool, and that wool, I know for sure if you rub your fingers or your palm on that wool, it will charge you. It will charge your palm electrostatically like nobody's business. You will make like this, and you will get the spark between two fingers. And I was thinking actually on this kind of self-inducing electrostatic charge on myself, and then testing it there. I did actually made this experiment, but not rub. I did rub my hand on normal sheet, but I'm not completely ensured that I was getting higher electrostatic potential on my hands from that rubbing. Just normal potential, like every object in my room. But I did finger the gate here on the 12 volts after the 1 kilo. I don't remember if I put my finger, if I was stupid enough to put my finger right here in the middle. Probably I did a couple of times, but this MOSFET that I'm having here is, like I said, and I will repeat it many times, it's extremely sensitive. It should have been destroyed already from my fingering on that 1 kilo if it was naked without this protection. And I believe this worked. And if I put my fingers like an idiot there, and I already did by using this tweezer, metal tweezer, by holding all these metal legs and components and soldering there, and even this soldering iron is having electrostatic potential on it higher than what I'm having there. This will include a little bit of higher transients, something there that can potentially destroy it, the interior of the MOSFET. So while I was working on adding all these diodes, I already introduced a lot of risk, and especially for, again, I'm repeating myself, extremely sensitive MOSFET, especially the gate of it. The gate of this MOSFET is fantastic sensitive. So far so good. I mean, it is still running correctly. Even with all my fingering, I did test it with my finger. I did worked on its gate quite extensively, I may add, and it's still working as it should be. Theoretically, I'm happy that I reached this stage, but in time I will be very sure. Time will tell exactly how good these contraptions that I did and that I buy here are. This is it. This is all the experiment that I wanted to show you, and it's very important to protect and be aware of the fragility of the MOSFETs in general. And actually, my ERFZ 44N, that you probably can read it there, are not as sensitive as this very small SMD MOSFETs. They are more durable. If I'm poking, if I'm touching the gate of the MOSFET, and consecutively, in the same time, the source or the drain with the gate touching, they are more resilient. They have some better construction. They have some already they have this protection inside them, this protective diodes. I have no idea how they are, but they are better. They are definitely better to manipulate with your hands. Although my friends from America and from England, they both told me every MOSFET on this earth is very susceptible to electrostatic discharge. So I should wear all the time this bracelet, this grounding wire on my hand when I'm manipulating them. And I'm starting to learn, slower but surely. When I was handling these MOSFETs here without my protection here, and I put them in circuit, they just worked without any problem. I even overstressed them, and they still worked fine. That's an important comparison to make. If you want an already built-in protection, probably that ERFZ 44 is better to use for testings. compare with these little fuckers that are just dying just like that. You know, that's why they are so cheap, because they have absolutely no protection and they are miserable in how sensitive they are. They are just miserable. I don't like them. How sensitive they are, too sensitive. I don't like them at all. But you learn, and this was a great deal for me to get to this point, to be able to create myself some kind of protection here with this Xenon diodes or these TVS ones that I specifically buy them for protection, but also for other projects as well. Okay, this is it. Thank you very much for watching. Thank you very much for listening. Also leave a like, because I didn't put any advertisements. I'm not advertising anything. My movies will be always free of stupid advertisements that I'm seeing on the entire YouTube. Is full of forced advertise. People are forcing advertisements in their movies, and they are just I don't like it. So in my movies you will always get the good stuff without advertisements. And thank you very much for watching and for listening and for staying with all this experimentation, with all this trouble that I got into. And I hope it's worth it for you. I hope you learned something new. Or if you didn't learn something new and you already knew all this stuff, at least you've seen another dude doing the right thing. I hope this is the right thing. I hope this is the most correct thing that you can do. I hope there is not another way of doing it that I don't know. But this looks like it's working, like it should work, and I'm very trustful it will be in the future. Again, I will this kind of protection will be tested in time, not in one setup that I'm doing it here. Right now, I just discovered how to do it in 2 ways, pretty much. But later, but in time, I will say how good these 2 ways are. All right, and I prepared a little 3D demonstration here, and yeah. All right, what we are seeing here is the interior of a MOSFET. You can see this very thin layer oxide insulator. This yellow one here is between the gate and the source, or between the gate and the rest of the transistor, pretty much. Very thin, as you can see. It's very, very, very thin, like paint almost. It's having the thickness of a paint application, like that. It's like it's painted there. That's how thin it is, and it's an extremely good insulator. Probably ceramic or glass, who knows exactly. And as you can see, as you can observe, the gate, which is this block here, this black block, you can see this gate is completely floating because of this insulator that is staying onto. This means if an electrical charge gets trapped on the gate, and actually I draw an electrical charge, it's here. This is the electrical charge that is building up on the, let me bring it a bit in front like that, is building on the gate surface that is floating, by the way, and is having nowhere to go. If it's trapped there, it is just sitting, floating with the gate, with this element. This element is floating together. Again, if this will ride this floating gate like on a boat, you know, this positive charge is floating on this little boat that is the gate, this element. And if this charge is high enough, if it's like this, is accumulating and is becoming too much, is increasing, and you know, increasing little by little, not like I did it here at once. But who knows? Nature is full of surprises. And if it's rising like that too much on the gate, well, if the difference between the gate and the rest of the transistor is too large or large enough, the voltage across that oxide could reach a critical level and destroy the oxide, which is this yellow paint, seen as paint, strut or substrate or whatever you want to call it. And since this oxide layer is quite thin, because it's needed to make a good MOSFET, having it that thin is important to be like that, to make a good MOSFET. It is also very easy to damage. Some MOSFETs are damaged by only a few volts, like my 2N7002 MOSFET. An ESD event can inject a lot of charge into the MOSFET, causing charge differences, resulting in a voltage across the oxide. So that voltage across the oxide has to be somehow limited, and that is what the ESD protection diodes between the gate and the source do. Even if you would take all precautions needed to prevent an ESD event, it can still happen and cause damage. Worst of all, the damage can be imminent failure, meaning there's damage but you don't notice it yet. The MOSFET works fine, but after some usage, hours, days, weeks, or even years, that damage might eventually become fatal, resulting in a broken MOSFET. So it is really important to have at least some protection against ESD. An article from Texas Instrument mentions that any kind of gate protection often comes at the cost of higher gate leakage, and that you may need to avoid gate protection diodes in low power equipment like smartphones or other battery powered devices. Most modern MOSFETs have some intrinsic ability to withstand ESD. If you store them properly and only handle them at an ESD safe workplace, they will be fine. In fact, Texas Instruments says that most MOSFETs have no extra protection at all, just their intrinsic ability. I'd say the rule is use MOSFETs with extra ESD protection when you know you must have it. The gate may be controlled by external signals or by circuits or networks that pass ESD from external sources. Button-controlled electronic switches are notoriously susceptible of ESD. Also remember that the protection isn't really at the gate. It's between two terminals. So it's between the gate, either source or either the drain. That's why I was very interested in finding a protection in both directions, if you remember. Exactly because of this detail. So the protection isn't really at the gate. It's between two terminals, doesn't matter which they are, and will protect from any situation where an overvoltage condition would exist between them. The source and the gate are thus equally susceptible. It doesn't matter where the heat comes. What matters is that the gate to source voltage is too high. Holding gate steady and hitting the source is equivalent to holding the source steady and hitting the gate. Thus, the protection extends to source and drain pins. Reverse polarity ESD pulses will be shunted across the channel by the body diode. Positive ESD pulses may cause trouble still, but the charge and energy needed to destroy the device while it's avalanching in forward breakdown is much higher than what the gate can take. As for why bundle the protection, just think about costs. Do you really want to have to add an ESD protector? You're already paying for a semiconductor device, and most of its cost is in packaging and testing. The tiny semiconductor die inside is almost free, less than 10% of the cost for a discrete device like this. Throwing in an ESD protection for the fragile gate is a no-brainer. It'd be most ridiculous not to. So why is not done in all discrete MOSFETs? The protection device has some non-ideal characteristics, adds capacitance and non-linearities that cause distortions. This is of no concern in many applications, but not all. The protection diode is not suitable when lowest gate leakage is desired, or fastest possible switching. Distortion may be problematic in some ARF application, but it's a very good thing most of the time. Curiously enough, ESD can be a hit from body through an insulating case. This happens often enough, especially with the chip cases. All it takes is there to be a tiny crack in the plastic, not hard to come by when dealing with handheld stuff or stuff kept in pockets, or just the natural gaps between separate plastic parts. Over time, the crack or the gap accumulates some wet salt or other junk from sweat, and it's like having your own very special ESD test setup. So I read a little bit of text that I find relevant to this problem, because this was my problem for a very long time. Like I already said a couple of times, and most probably other people are having MOSFETs in their hands and they get destroyed and they don't know why. And this is a very good tutorial about it. How to behave with a MOSFET, how to think when you have a MOSFET in hand. What problems is putting in front of you. With this little adventure here, let me switch to camera here. Let's see if I'm playing it now. I will give you this last fly around, because it's cool, and I will leave you with it. That's it. Okay, I hope you like my little model here, my little 3D model that I made it in, by the way, in 3ds Max 7, which is a very old version. It's not an old application, because this application is still a big deal even today, and it reached a very high number in its version, probably 24 or something is by the year is running. It's changing its versions. So, but even if it's this very old version from 2007, this 3ds Max 7 is from that times. It's my favorite 3D tool to work with, because I learned it quite hard. It was to learn it, and now I'm just playing in it. I know some stuff about it and how to use it. Okay, that's it. Thank you very much. Bye bye. Okay, thank you very, very much for staying with me, for listening, for watching, for understanding, and I say to you goodbye from your favorite artist electronist, Mr. Q12 here. I say to you bye bye and see you later. Bye bye. And wear your grounding bracelet when you're working with MOSFETs in general. Don't forget it. All right, bye bye.